airdrops enable governance. The idea that people who represent the protocol or care about the protocol can vote on the future of the protocol. However, the issue is that if you can see how everyone else is voting, you yourself might be influenced by them. If you even see that someone voted, you might be influenced to spend more time or less time voting on that proposal. In addition, whether or not you sell your tokens can be a controversial issue, and whether or not you vote can also be completely public, which is maybe a feature that we don't always want. Introducing Stealthdrop, the first way to do anonymous governance via zero-knowledge airdrops. So how does this work? You can imagine that the airdropper first publishes a Merkle root of a Merkle tree of eligible addresses, just like a normal airdrop. However, instead of claiming from your eligible address directly, you claim from this anonymous address. So in this case, Aayush.eth is in the eligible addresses, but instead I'm going to use my anonymous address to generate a ZK proof that represents that I am in this Merkle tree. Then when I send this to the contract will make sure I can't double spend by adding me to a nullifier list, and I'll receive my coin to the anonymous address instead. So again, your airdropper publishes the Merkle root, you create the zero-knowledge proof, and the on-chain contract verifies that and awards you the token. Now, what exactly is this zero-knowledge proof proving? Well, we want to keep all aspects of our original identity completely private. So that means our signature, our public key, and the Merkle path have to be private inputs. However, what we do need to make public is all the aspects of the airdrop itself that the contract can check. Things like the Merkle root being the same as the Merkle root released by the airdropper, the message that we're actually signing being the same message that they requested we sign, as well as our nullifier. The ZK snark just verifies that all the information we inputted is actually calculated correctly. The Merkle path, the signature, the nullifier, and the message that we sign. Now you can see a demo here where first we connect the original wallet, and then we can swap the wallet in MetaMask. Usually you would probably use a different computer or a different website, a different tab. And then you will generate the proof that you actually own that original address that you entered, which will eventually claim and be sent from the anonymous wallet. Here, the proof is cached, so it loads very quickly, but in reality, the proof takes a couple of minutes. Then you can claim the token to your anonymous address. Wonderful. You can see the transaction. Cool. We also battle tested our airdrop idea with 100+ claims from the 0xPark and HackLodge community. And Nalin will dive into more details about how we scaled that. So one issue you guys might have noticed is that for our nullifier, we use a hash of the signature. However, these signatures are non-deterministic, meaning that even though you may have signed with deterministic ECDSA, a verifier of that signature cannot actually verify that whether it was generated deterministically or not. And as a result, this would allow someone to generate an infinite number of signatures and claim as many times as they want. So there are a couple ways to fix this. The easiest one is to just run the priv-to-pub circuit in your browser, in which case you won't have to rely on signatures at all. And instead of your nullifier being a signature, it can just be a hash of your entire proof. There are also other ways that we can get around this issue that require slightly more complex technology, such as releasing multiple lists or using MPC to generate randomness. And we're happy to talk more about those solutions if you come up to us afterwards.
So I'm going to talk a little bit about sort of the internals of building Stealthdrop. So Stealthdrop was built during this program called ETH HackLodge, which is just like a hack week. So one of our goals at the time was to sort of maximize the amount of learnings you can do and just like have fun. So for instance, here's this slightly questionable commit I made at 1 a.m. Anyway, so when we started working on Stealthdrop, we saw that Circom2 had been out for like a couple months at this point, and it seemed like the shiny new Rust compiler and all these cool like tricks and things like that. So we were like, okay, let's try using Circom2. So when we started using Circom2, it turned out the witness generation had bugs in it, and so at this point, we could either write Stealthdrop circuits or fix the Circom2 itself. So we decided we should actually fix Circom2. So we took a detour and ended up fixing some of the bugs in Circom2, and a lot of those PRs were also merged, so all of this is public now. And the Besides this, one of the big themes of using ECDSA in a snark is that the circuit is huge. It's like 9 million constraints, and along with that comes like all these problems of like scaling, and you have a proving key that's like 6.5 gigabytes. So how do you even run these proofs? So the solution to that is using a remote snark prover for now. And we ended up writing this really neat ZK node server, as we called it, which has like a queue and does like resource management and all these things sort of neatly, and is just like a package. In fact, the ZK pairing team, which we'll demo tomorrow, is using a fork of this node server, which is super cool. Another idea at the time, so we really wanted to do these proofs in browser, but it just like, with these huge Z keys and these huge circuits, it just didn't seem possible at the time. But one of the ideas we had was, what if we take the proving key and chunk it into small pieces, load these pieces in browser, do whatever computation needs to be done, and just like delete it or like re-download it or do like some kinds of operations with it. So we ended up writing this patch for Snark.js, which we call like chunked Z keys. At the time, it does reduce memory usage by a lot, but at the time, even with this, it was not, the ECDSA circuits are not good enough for doing proofs in browser. But simultaneously, during the last couple months or something, the ECDSA team has been working on optimizing the ECDSA signature verification circuits, and they optimized it by like a factor of 6x almost. And now it turns out that combining these two optimizations, the ECDSA signature verification and chunking of Z keys, you can actually prove ECDSA signatures inside a ZK snark in your browser. And in fact, there's another team in 0xSpark community working on ZK Reddit, which is planning to use this combination of patches. Another cool thing by like poking internals of Snark.js and Circom and all this stack, we actually ended up discovering a couple of optimizations in how Snark.js proofs work. And in fact, one of these was this caching of Z-key curve computation, which almost cuts down by like a second flat for any circuit in browser proving. So it turns out for like smaller circuits, maybe like 1,000 constraints or something, this is in fact like a 30% of the time of your computation. So it is like a pretty massive improvement. And actually, this is an open PR right now, so I know there's people in this room that can help us get this merged, so wink, wink. Yeah, I think that those are like sort of the high-level overview. There's a lot more detail in the README of our repository, and there's all our Twitters and all of that. And thank you to everyone in the 0xSpark community for this idea and helping us execute all of this together. Thank you.